guys, welcome to Bio 112 Online, your home for biology education. We have come to the last lecture of the semester, Osmoregulation. As you will recall in our last lecture, we are talking about the nephron, and the nephron is going to be the functional component of the kidney. The nephron is going to be responsible for filtering fluids from the blood, resorbing components of that fluid that the body wants to keep, secreting additional compounds that the body does not want to keep, and then excreting that filtrate as urine. There are four main components to the nephron. First, there is Bowman's capsule, which will filter the fluids from the blood and collect the filtered fluids. There is the proximal tubule, which will move sodium chloride and water from the filtrate into the blood. It will then have some level of secretion going on where additional compounds are added to the filtrate. The filtrate then moves into the loop of Henle. Within the loop of Henle, as you move down the descending loop of Henle, you have additional water resorption. As you move to the ascending loop of Henle, then you have salt resorption. Finally, you move into the distal tube for polishing, where you have additional products that are secreted, such as potassium and hydrogen ions, and some small amount of water is still resorbed again. That fluid then flows into the collecting duct. Now recall, we also had two general forms of nephron. We had the cortical nephrons and the juxtamedullary nephrons. The cortical nephrons, as we've described before, remain in the cortex. The nephrons that are in the cortex but have a component that goes into the medulla are referred to as the juxtamedullary nephrons. In the case of the cortical nephrons, most of the resorption that's going on is occurring in that proximal and distal tubules. For the juxtamedullary nephrons, they have the added benefit of a highly selective and sensitive loop of Henle. The key thing that drives this is going to be an osmolarity gradient that exists within the medulla of the kidney. Recall that the medulla is going to be the innermost zone of that kidney, relative to the cortex on the outside. In the case of the loop of Henle, you have the nephron extending into that much more saline environment, that environment that has a much higher osmolarity. This higher osmolarity for the descending loop will drive that resorption of water. In the ascending loop of Henle, as the filtrate moves into progressively less and less salty areas with lower osmolarity, then facilitated diffusion will take place as salts move out of that filtrate. The distal tubule would then be found within the more fresh portion of the kidney. But then you also have the collecting duct, and that collecting duct will also move into the medulla of the kidney, and that's going to be significant in just a moment. Recall also that you have a series of blood vessels that are feeding this kidney. Recall also that you have a series of blood vessels that are feeding this nephron. The afferent arteriole will be a branch of the renal artery that supplies the nephron with blood. That will then feed into the glomerulus and then continue on in the form of the efferent arteriole. In the efferent arteriole, the peritubular capillaries will move in amongst the distal and proximal tubules, resorbing the fluids and salts that were resorbed by those portions of the nephron. You then move into what's referred to as the vasa recta, which is going to be a series of capillaries that will resorb the salts and the fluids resorbed by that loop of Henle. Now, here's where the juxtamedullary nephron becomes so special. It has the ability to absorb a significant amount of fluids simply because it moves into that medulla. It does so by the effect that we refer to as the countercurrent multiplier system. The juxtamedullary nephron will use energy to generate and maintain an osmolarity gradient within the medulla of the nephron. And that osmolarity gradient will then drive the level of salt and water retention provided by the loop of Henle and the collecting duct. So if we start off and consider the osmolarity of the filtrate as it moves into Bowman's capsule, you will see that the osmolarity of the filtrate is the exact same as the blood, which makes sense because it was just filtered from the blood. As you move into the proximal tubule, you have the resorptions of salts that also leads to the resorption of water in the same location. Because that resorption is proportional, then the osmolarity doesn't change. The volume does change, however, and about 70% of the fluids that are filtered by the glomerulus in Bowman's capsule are resorbed in that proximal tubule. You then move into the descending loop of Henle. This is where the osmolarity starts to change. As you move further down the descending loop of Henle, then the filtrate becomes progressively more and more salty. Once it turns the curve and starts moving up the ascending loop of Henle, then you have the transport of salts out of that solution, and therefore it becomes progressively less and less salty. Now recall that the movement of water in the descending loop of Henle is due to the presence of aquaporins and is simply being driven by osmotic effects. Recall in the thin portion of the ascending loop of Henle, it's being driven by facilitated diffusion, simply a difference in salt concentration from the filtrate to the interstitial fluid and the blood. Finally, when you get to the ascending loop of Henle, you have the movement of salts from the filtrate into the interstitial fluid and blood being driven by active transport due to sodium-potassium pumps and the sodium-potassium chloride cotransporter. Taken together, these components will set up what we refer to as a countercurrent multiplier system. That's where you have active transport in that one region of the loop of Henle driving the concentration gradient in the entire region. If we were to look at that concentration gradient, we would tend to see it near the proximal convoluted tubule that the osmolarity is about 300 milliosmol. That quadruples to about 1200 by the turn of the loop of Henle. It then turns back the other way to get back to 300 once it reaches the thick portion of the ascending loop of Henle. But because of that active transport, it actually gets lower than that, down to about 100 milliosmol. So what's really going on here? Let's think about it from the perspective of the filtrate. You have the filtrate moving on the descending loop of Henle. As it's doing so, the osmolarity of that filtrate is lower than that of the surrounding blood and interstitial fluid. As a result, if it's 400 milliosmol in an area that is 500 milliosmol, it has less osmolarity, and by simple osmosis, water will leave that tube. As it continues into a progressively more and more salty 600, 700, 800, the filtrate finds itself in a progressively more and more salty environment. Every millimeter that it moves, it finds itself in a progressively more and more salty environment. It loses water at the same time, meaning that you have a consistent difference in concentration between the blood and the filtrate. We see the same thing as you're looking at the ascending loop of Henle. You go from a highly concentrated filtrate of 1100 milliosmol, but as it's moving up, it finds itself in 1000 milliosmol, which means that you have facilitated diffusion, moving salt ions from a higher concentration to a lower concentration. It moves it up a little bit, and now it's still more concentrated than the interstitial fluid around it. and so it loses more of its salts. It progressively moves up the ascending loop of Henle, and each millimeter that it moves, it loses more and more salts because the interstitial fluid around it and the blood around it are all slightly less salty than that filtrate. Now, this is where the importance of the vasa recta comes into play. Because in this case, the blood itself is actually becoming more salty and fresh as you move down the ascending loop and up the descending loop. You say, what is that? How's it moving up the descending loop? This is because it's moving countercurrent, or the opposite direction of flow, to the filtrate. If you're thinking about it from the perspective of the blood, as the blood is moving down the ascending loop, you initially have some additional loading of salts due to active transport. That makes that blood get slightly saltier. You then have that blood moving into the more salty regions. In that case, it's constantly getting saltier this time because it's just slightly fresher than the surrounding portions of the loop of Henle. It continues on until it reaches the bottom of the loop of Henle and turns the corner. As it turns the corner now, we again have a countercurrent situation where the blood is moving into areas that are progressively getting fresher, and you have water now diluting the salts that are in the blood. About 25% of the water that was in the filtrate within a juxtamedullary nephron actually gets resorbed in the loop of Henle. Added onto the 70% that was already resorbed in the proximal tubule, and that gets to about 95%. There's an additional amount of resorption that can take place that goes on in conjunction with the distal and the collecting duct. The function of these now is going to be regulated by hormones. The net effect of this, when the collecting duct and the proximal tubule are active, is that about 99 or more % of the water that was filtered are resorbed in the body. However, any of the urea or other metabolic wastes that were present in the blood are now present in the urine at 100 times their original concentration. This is going to be critical for mammals in dry areas, and is actually going to be critical for vampire bats. Now, vampire bats have a conundrum. That conundrum is that first, they fly, and second, that they drink fluid. Well, the fluid becomes bad because their main diet comes from drinking fluids, and fluids are heavy. And for flying, it's all about being as light as possible. In the case of the vampire bat drinking its blood meal, it needs to very quickly process and excrete that fluid so it can fly away. Of course, once it's done drinking, it has the opposite problem. It's not taking in nearly as many fluids, and if it continues to excrete at that prodigious rate, then it's going to dry out and die. That becomes another problem. As a result, vampire bats have to have a very high level of control in the amount of fluids that they are processing and excreting. This brings us to the control of the nephron. The volume of urine that's being produced and the osmolarity of that volume being produced is being driven by hormones. The first of these we discussed earlier in this semester when referred to as antidiuretic hormone. This, as you recall, was made in the hypothalamus and then stored and secreted by the posterior pituitary. Antidiuretic hormone will travel in the bloodstream until it reaches the collecting duct and distal convoluted tubule of the nephron. Its main purpose is to enhance the level of water resorption by the distal tubule and collecting ducts. It does this by increasing the permeability of those regions of the nephron. As a result of the water loss from that filtrate becomes progressively more saline and have a higher osmolarity. As you recall, antidiuretic hormone is going to be stimulated by increases in osmolarity in the blood. That is detected by the hypothalamus, causing the release of the antidiuretic hormone. As a result of that antidiuretic hormone, once it reaches those regions of the kidney in which it is active, it will hit a G protein coupled receptor. Once it hits that G protein coupled receptor, it will then activate a signal transduction pathway. In this case, both the cyclic AMP and the IP3 pathways. In doing so, it will stimulate the production of aquaporins. It will also result in the activation of storage vesicles for aquaporin. As you drink additional fluids, then you will find that the amount of osmolarity of the blood decreases back to normal, leading to a negative feedback where less of the antidiuretic hormone is being produced, leading to less aquaporin being placed on the collecting duct and the distal tubule. The net result of this then is that less water would be absorbed. We can see this happen anytime we're going about our normal days. As we drink a lot more water, then we find ourselves excusing ourselves to the restroom more often. There's other times where we might be consuming beverages which might also have a further impact on this, particularly in the case of alcoholic beverages. Alcoholic beverages, and especially the alcohol within them, will block the calcium voltage-gated channels in the anterior pituitary. As they do this, they will decrease the release of antidiuretic hormone, which means even if the blood does get saltier, then the body will not respond. As a result, it will continue to lose fluids regardless of whether or not the body should be retaining them. So in that case, you may be losing more fluids than are being consumed in the alcoholic beverage. And as a result, the body has a tendency to dehydrate on such events. The other main form of hormonal control is referred to as the renin-angiotensin-aldosterone system, otherwise shortened to the RAS system. The RAS system helps maintain blood pressure and volume of the blood in homeostasis of the body. It does this by regulating the resorption of salts in the collecting duct. The juxtaglomerular apparatus releases renin in response to low blood pressure. So basically, if your blood pressure drops too low, the juxtaglomerular process will release renin. So what does renin do? Renin will then act as an enzyme in the blood and will convert a protein called angiotensinogen into angiotensin. Once it's converted into angiotensin, it gets converted into angiotensin 2. Angiotensin 2 then raises the blood pressure, causing vasoconstriction of arterioles and arteries. Angiotensin 2 also will stimulate the release of aldosterone from the cortex of the adrenal gland. Aldosterone will then cause increased amounts of production of sodium-potassium pumps and sodium channels. In that case, the collecting duct and the distal tubule will begin to resorb more salts if done in conjunction with antidiuretic hormone. It means that the collecting duct and the distal tubule are now resorbing both salt and water and are basically acting as a new version of the proximal tubule. In conjunction, those two hormones, ADH and aldosterone, can massively increase the level of water resorption in the body and prevent water loss back to the environment, maintaining homeostasis. And that's it. Not just for a discussion of osmolarity in the kidney, but also for Bio 112. You have now completed Bio 112. I want to thank you guys for being really awesome this semester. Bumps and warts though the semester may have had, I hope you have a wonderful semester, and I hope to see you next year for the next term of biology. So, until then, stay safe, stay healthy, and I'll see you later.